Hello again, everyone. My name is Chris Dorn. I am a technical sales specialist for ITM Instruments. Thank you for joining us today for this webinar via our ITM University. Today's topic is pressure calibrations with Fluke. During the presentation, we're going to ask you to kindly mute your microphone. The presentation should last anywhere between 40 and 45 minutes, and we'll have a time allotted at the end for any Q&A. We definitely encourage you to submit questions at any time during the presentation, and you can do so using the chat feature. As mentioned, we'll get to your questions during the Q&A portion. ITM Instruments has been working closely with Fluke for many years. We pride ourselves on being a leading distributor of Fluke. This is a result of our dedication to offering you our product expertise, service, and competitive pricing. We're getting started today. Our presentation is presented by Ken Reeves from Fluke. Ken is Fluke's territory sales rep based in Alberta, Canada. He has over 31 years of technical test equipment sales, which include over 20 years working directly with Fluke. Ken, I'll turn the presentation over to you.
Thank you very much, Chris. Hope everybody's having a great day. If you can see my screen, we'll get started. We have a fair bit of content to get through today, and I want to give you the opportunity to ask as many questions as possible at the end. So today's presentation, we're going to cover off the topics that are shown on the display right now. I'm not going to read through them all, but ultimately at the end of the day, end of our hour together here, we're going to hopefully raise your awareness of pressure calibration, some best practices, some tips and tools, and some other ways to maybe approach the calibration of pressure that you are either doing today or may want to consider doing in the future. So let's talk quickly about pressure calibration in general. So what is calibration? Calibration is the practice of comparing a known standard to an unknown standard, and you make a comparison between those two. The one that is more accurate is considered to be the reference, and the one that's being compared to is what we call the DUT, or unit under test. You typically do a calibration to find out how far away you are from a known standard, and we just keep that in consideration and understanding that as we do these pressure comparisons, that's what we're going to be talking about when I mention the word calibration. Occasionally, the conversation will lend itself to what is traceability. Traceability is actually probably more easily understood as a paper chain between the standard that there is within a country down through the different layers of accuracies into the equipment that you take out into the field. The units that we sell from Fluke have a calibration standard or accuracy from the factory, and some of those units are provided with a traceable certificate. If you need something that's up to date and traceable, ITM has standards and capabilities to do that in their lab and be able to support you on that. Traceability in itself, the comment down here in the bottom, and you should be seeing my cursor moving, traceability in itself does not ensure accuracy. You need to pay attention to the accuracy of the process that you're looking for and what calibration gear you're bringing to that. There is an industry standard kind of in place that you should maintain a minimum of 4:1, but preferably somewhere in the 10:1 range in terms of comparison between your standard and the unit under test. Now let's quickly talk about pressure. This is the second part of a two-part series. We did one on temperature as well. And pressure, unlike temperature, is not a primary standard for SI. It's actually what they call a calculated standard. And what they do is they use some existing standards that are in place for force and area or dimensional measurements, and then use the formula where you have force over an area to come up with a calculation for pressure. In the SI system, the unit for pressure is Pascal, and it's defined as a Newton of force per square meter of area. So again, it's not a system base unit, but rather a derived unit in the SI system. The units that we use for pressure are varied, and they're almost endless in some respects, because there's many different ways to describe what that force is and what the area can be described of. Just using simple units, we have area being able to be described in inches, in feet, in meters, and even on the force side, there's pounds and kilograms of force. So when we mix and match all of these, they become, as you see listed down there, just a few of the different units that you find. There's a fun fact that I've highlighted here. For instance, the word force has typically been eliminated from the idea of what pressure measurements are. So it gets assumed that that's what we're talking about. But for instance, PFSI is just what we call PSI today. They take the word force and remove the letter F from that. And so many times you will see pressure described without the force component, but it is always there. Let's have a quick discussion about pressure and temperature and volume and how they all interact with each other. On the previous slide, I don't know if you noticed or if you read it on your own, but pressure is the force exerted perpendicular to a surface. And what the force they're talking about is the molecular force. So all the molecules. When we have a fixed volume, we'll have a fixed quantity of molecules. And if we reduce that volume, we are actually creating more pressure because the molecules would be more molecules exerting force on those surfaces. Similarly, if we have a fixed volume and we increase the temperature, the action of those molecules will press against the force of the inside of that container and create more pressure. So there's two ways you can create more pressure, either increase the temperature or you can increase the volume. If we reduce the volume, we actually reduce the pressure, and if we reduce the temperature, we'll also reduce the pressure as well. So let's talk briefly about the different types of measurements out there that we have for pressure. The one that we're probably most familiar with is gauge pressure. Gauge pressure is the pressure that's relative to the atmosphere of the day. It's a positive value for pressures above atmosphere and a negative pressure for pressures below atmosphere. So if I were to say my car tire has 32 psi in it, that would be the pressure of the day, and it would be 32 psi higher than whatever the absolute pressure surrounding the outside of that tire. And if you drive in Canada, you know if the weather gets colder, the atmospheric pressure will reduce a little bit around your tire, and then therefore, increase around your tire, and then therefore your pressure drops in your tire because the molecules inside reduce. The atmospheric pressure is typically, Chris, is everything okay with my webcam, or should I shut it off?
You know what? For now, let's shut it off.
Yeah, I'm getting some errors on my side. Just give me a second. I'll go to my webcam and turn it off. Sorry for that, folks.
No.
It should have actually turned itself off, and it hopefully stays that way. Okay, so the atmospheric pressure is the force exerted by a column of molecules that are being acted upon by gravity. And at sea level, it's described as 1 atmosphere, which is roughly 1.1325 bar. And they are close enough that a lot of times people will say a barometric pressure is the same as atmosphere, and they get used interchangeably. There is a small difference, but for most practical applications, unless you're dealing in a lab environment, that's typically what gets said. The absolute pressure is the sum of both the gauge and the atmosphere. So to be able to describe this, it's easier to understand if we're talking about if I had 0 absolute, that mean I have 0 gauge pressure and 0 atmosphere. And the easiest way to understand that would be in a complete vacuum, which we equate to outer space. So if I have an absolute pressure, it would be the combination of those two. So as my pressure goes up from 0, I can never have a negative absolute. So if I have a positive absolute pressure, it's a combination of those two. And if we can determine the atmosphere, then we can determine how much other pressure is there, which would be the gauge left over. The differential, that's the difference of two pressures. Typically, it's lower pressures that are being measured in these applications. However, we can have some pretty high static pressures and still try to measure a differential. So an example of that is if I had 1,000 pounds on one system and 1,001 pound on the other, I would have a 1 pound differential with some pretty significantly high static pressures. I've alluded to the static pressure. That's the relative pressure of a system. And it's being used to avoid the ambiguity with regards to gauge or differential. It just describes what the pressure is statically pressurized at, what the system is statically pressurized at. I think I'm gonna move my cursor. It gives me the ability to change screens. Here we go. And here's a few more. So we've got vacuum. We've kind of alluded to that already. That's the absence of molecules. And so therefore with no molecules, you'll have no pressure being exerted. And the interesting thing is that we've actually achieved a higher vacuum on Earth than they did in interstellar voids. So the Large Hadron Collider had the ability to pull a 10 with -6 zeros at the end of it of a millibar. So very, very, very low pressures and approaching ultimately pure vacuum. Compound gauge, just like the one shown on the picture there, that's a gauge that we simply use to describe both positive and negative pressures on the same device. And then a draft. Draft pressure is very similar to a differential in fact, sometimes they get confused or used back and forth. But really the word draft is representative of very, very low static pressures. So an example might be if you've, pressurized a clean room so that no, external gases come into that room. You've created a slight pressure difference, and that differential is being measured by draft pressure. Okay, so we've gone through all the different types of pressures that I can think of and that were on our list. But just to give you a quick overview, pressure is everywhere. We use it all the time. We have it in our air and our tires of our vehicles. There's a picture of a guy using a pressure washer to clean the side of a building and got a little creative with it. But pressure and temperature together will work in our favor when we are attempting to make process actions happen. So if we have a specific reaction that we need to have at a certain pressure and a certain temperature, we need to be able to control those. So if it's a simple case of making beer or a case of making some chemicals or some part of your process, having a good control over that requires the ability to calibrate pressure. And again, getting back to a primary standard or something through traceability. So let's talk about the different types of calibration gear that are out there and some of the 7 tips that Fluke would like to bring to your attention. So right out of the gate, there's really 2 types of media that we're talking about. There's gas and pneumatic and liquids. First of all, I'll talk about the gas and pneumatic. The gas pneumatic calibrators will compress the existing atmosphere available to us, or they've already been pre-compressed, like in the nitrogen bottle on the lower side there. And they are used typically for lower pressures, typically 600 PSI or less. You can use them for higher pressures. That nitrogen bottle is, when it's fully charged, could be in the 2,700 PSI range. And the pneumatic hand pump that's beside you from Fluke, that one can get you to 3,000 PSI, which is pretty amazing when you're talking about being able to compress that much air from the atmosphere and keep it isolated and be able to create a pressure calibration that's nice and clean. That's the primary use of a gas or pneumatic calibration when you get above 600 PSI, is that people are wanting to keep systems clean. Below 600 PSI, it's just actually easier to use nitrogen or pneumatic handheld hand pumps or whatever the case may be. The trick on all of this is to make sure that you keep your systems clean. And we'll talk more about that when we get to the liquid side here. So liquids, we can compress liquids. They have lower volume with liquids. It allows us to get higher pressures. We're not actually, theoretically you can't compress a liquid. So we have the ability to compress liquids such as oil, water. If you're using a hand pump, sometimes people in the field will use windshield washer fluid or hydraulic oil. Oil, as it says there, is preferred because it's less corrosive and it actually acts as a lubricant to the systems. The trick with oil is that it can get pretty messy pretty quick. So if you have a little spill, you have to clean up your equipment, make sure it's nice and clean. If not, that will attract dirt, and then you can transfer dirt back into the system. And if anybody has any complaints about hand pumps in general, it's that they have a tendency to, the seals break down, they don't hold pressure, those types of problems. And a lot of that has to do with the actual contamination and the methods of contamination within the systems and how the pumps themselves are designed to keep themselves clean. Below 10,000 psi, they're fairly easy to use. You can still use your hand to pump them up. I have to admit, you have to be a bit of a Herculean type person to get above, say, 5,000 psi, but it's possible. But as you keep your pressures lower on hydraulics, it's still the safest way to get there. If you have any pressures that are above 10,000 psi, and for the most part, Fluke doesn't make much equipment that gets up there, but you'll notice that it becomes very specialized pieces of equipment. You may have jack pumps, you may have other leverage capabilities. So it becomes pretty specialized equipment to be able to get up there. You can have also very, very low volume hoses to be able to get to the higher pressures. When you get out into the field and you're doing field calibrations with a hydraulic pump, typically you're introducing the potential for the compressing media that you're using, oil, water, windshield washer fluid, whatever that case may be, that has the opportunity to enter into your process if it's not cleaned. So you can create cross-contamination between your unit under test, either your transmitter or whatever it is you're trying to calibrate. And then when you reconnect it back up to the process and it's intended to carry something other than oil, you may have contaminated that. So those are things that are kind of outside the scope of the conversation today, but again, you should probably pay attention and be aware of it. Let's talk about stability and getting the right resolution. So we've already talked that volume changes will result in some pressure changes. That's directly connected. But if you have a pump that's leaking, therefore it's changing the volume. That's really what the problem winds up being. And it releases maybe too much pressure or too much volume when you're trying to make adjustments. Also, there's another, fairly well-known phenomenon, but if you were to pressurize a pump with a tube attached and block it down, you may see that your pressure starts to drop and you're looking like, is this pump leaking? What's actually happening is the tubing is starting to swell under the pressure that's there. So it's a toss-up or a balancing act or a compromise between how rigid you want that tubing and how flexible you need it to be for your application. Having good tubing attached to your actual hand pump will improve your ability to keep stable at pressures when you lock them down. Again, the number of molecules a leak in the system creates a pressure drop. There's another comment here about having too much tape. Teflon tape itself, we'll talk about it a little bit more in a few more minutes, but Teflon tape is really just a lubricant. It's not a sealant. A lot of people will ask for, I need the sealing tape or whatever the case may be, and it's not intended for that. It's intended to lubricate those fittings as you're tightening them down with your wrenches. So they don't do the job of sealing that joint. It's typically the way the fittings are designed. Another way that the stabilization can get problematic for you is temperature changes. So if I were to take a hand pump out of a nice warm shop and then take it out into the field, just the temperature changes of that pump itself will create effects on the equipment. You may have the pump get slightly, change its dimension slightly and start leaking when it gets cold, or it might get stiff when it gets cold. The process temperatures may be elevated, and if you're measuring it with a pressure gauge, those temperature changes might result in errors in the initial part of calibration. Again, fluid temperatures are a part of that, and it gets a little bit difficult to control, especially with your gas and pneumatic equipment. So gas and pneumatic equipment, again, volume has a lot to do, and temperature has a lot to do with how pressures are created. And it gets a little bit tricky when you have even something simple like a pneumatic hose laying in the sunshine. If you lock that system down and the sun came across it, you might see a temperature rise that you weren't expecting. So it becomes hard to control. And let's talk quickly about some lab equipment. So Fluke has a whole division within our company that sells lab equipment, and they sell deadweight testers and gauge comparators and whatnot. It's not typically your field type equipment, it's more for a bench, but they have very excellent, well, first of all, the labs themselves are excellent environmental controls, and then they have a great media control, and contamination is eliminated or very closely eliminated. We have physical dead weights, pumps, and comparators, and they're excellent for these types of applications. And pressure controllers, that's something I want to bring to your attention because we've further on in this discussion, you'll notice that we've actually been able to take some of our lab equipment into the field through pressure controllers. So what a pressure controller is a digital device that controls the pressure and automatically will compensate volume for pressure and temperature changes. So we have these very expensive. ITM actually owns a few of them for doing pressure calibrations in their labs across Canada. And they have these pressure controllers that we've been able to take kind of the heart and soul out of the product and drop it into a portable piece of equipment. We'll talk more about that later though. So again, hand pumps are the go-to tools. Again, they have a variety of issues, and controlling these elements all have to do with their own challenges. This is a screen I want to bring to your attention. When we talk about calibration, there's potentially a little bit of confusion between accuracy and resolution. Sometimes people think that if they have more digits, they have more accuracy. Having more digits is like a better set of binoculars. You can see a little further, but are those numbers that I'm giving you actually of value? And what I would suggest is that for pressure calibrations, especially if you're introducing people in the field that maybe aren't used to doing pressure cals or they're new to it, we want to try to keep the resolution to, I'm going to say the minimum, but the minimum with regards to accuracy, so how they work with each other. And if you say, for instance, you wanted, the example there is you want to calibrate a 15 PSI, you should, if you want to try to achieve 10 times more accuracy and you have that capability within your device, then adding one extra digit will allow you to still see it from a resolution and an accuracy point of view. And what winds up happening is if I put 4 more digits after that, those digits eventually will just be floating around and jiggling, and they're not valuable. They're least significant digits in the calibration cycle, but they can create problems where people are trying to adjust them out, and it's just impossible. So we recommend you keep your digits to a minimum with regards to comparing it to accuracy. Don't sacrifice your digits for accuracy, but don't put too many in place if you don't need them. Okay, I talked earlier about tape. There's a little tech tip on the bottom there about the different types of tape that are available. It could be used as a quiz if you wanted to ask your techs back in the shop. But often the unit that we're testing is very dirty. The applications that pressure systems are expected to operate under, there may be steam, water, they may be subject to dirt and dust, and that dust can be in the form of small pieces or large particles like wood chips. There's all kinds of different types of contaminants. So taking the time to clean where you're making your connections and the actual surrounding area a little bit it's not something that you should take lightly. It doesn't take much to get into your system to create problems. And so we highly recommend you take some time to clean it off. You can either use compressed air or some chemicals or rags or whatever the case, but it's worth cleaning. That includes cleaning off any tape that was left behind from a previous connection. If you are going to use wrenches, make sure they're the right ones and that you use a backup wrench. A lot of people will just grab a wrench. I've seen people use a digital pressure gauge that costs them a couple of $1,000s and just put it on by hand and not use a wrench, and they can rip the fittings out of them. We've done our best to beef up some of those pieces of equipment, but you really shouldn't be using anything other than wrenches, the correct wrenches to make tightenings on connections. If it's leaking still after that, then you have a fitting problem. Protect the calibration standard. So inspect your pumps regularly, protect the pump with a case during transportation. I've seen so many people just wrap the hoses with their pump and just throw them in a bag, and at least they're throwing them in something. But if you have a dedicated case for it, that's, we have the ones that are like plastic molded that will hold the pump in place. Those are excellent for transportation. Keep your cleaning materials and your spare parts with the pump. Sometimes people have them back in the shop, they'll get out into the field and it's like, oh, I need this part fixed, and then they got to go back and they're just wasting time going back and forth. Use filter and liquid traps. We have a little inline filter in the picture up there. It's just an inline filter that catches, dirt and media and whatnot. We have liquid traps for liquid pumps, and they're also really good at just keeping the media clean in terms of when you're connecting your standard to your unit under test. And inspect those filters on a regular basis. Alrighty, I'm just going to grab a quick glass of water here. Let's talk about the importance of exercising. And just like it says, they're not just you, but the unit under test as well. So if I'm a pressure gauge and I've been telling you that my pressure is 100 psi, and but I'm scaled from 0 to 200, but I've been doing 100 psi all the time, maybe a couple, 2 or 3, 4 or 5 psi differential all the time. And then you come up to me and say, okay, go to 0, go to 200. Like that, physically, there's mechanical systems, either a board on tube or a diaphragm. And if they haven't been moved for a while, they will be very resistant to that move, very, very resistant to that move. So if you were just to come up and drop it to pressure to 0 and go to 200, there's a good chance that the actual unit under test won't respond correctly. So we recommend that you cycle it, called exercising, typically 3 to 4 times at the beginning of a calibration cycle and prior to the as found. And the reason we do this is, again, they have mechanical memory, and we want to make sure that we give the chance for the unit under test to go through its full range of motion, so that when we go pressurize it up one way and then back down again, the opening here that we see in the measurement value is reduced to a minimum, and we call that hysteresis, and we want to eliminate that as much as possible. Final note here, it's kind of interesting. Your final calibration should be representative of the actual usage of the instrument and considered a cardinal point. In my previous example, at 100 psi, I would consider that a cardinal point. But if I was interested in a pressure calibration, and say, for instance, even though it's spanned from 0 to 200 psi, but it really runs somewhere between 85 and 115, then I might actually do a 5-point cal rather than doing 0, 50, 100, 150, 200. I would consider doing 0, 85, 100, 115, and 200. And then that way I'd be able to, more accurately describe what's happening in the middle span or what the actual usage of the device is. In our world, we call those custom calibrations, and it's something we can accommodate fairly quickly and easily. So if you've ever tried to calibrate a high accuracy analog gauge, or maybe even just an analog gauge that's 1/4%, when you pressurize it up and you're trying to, make a measurement when the needle is between 2 points, if you get 3 or 4 different people, they'll probably have 3 or 4 different answers. So what we suggest you do is, rather than say, I'm going to calibrate this gauge at 100 psi and the needle is not quite at 100, I'm not sure if it's, just below or just above, what we suggest you do is take your pressure until the needle points directly on the point of that gauge, and then record the source pressure. That source pressure is going to give us the ability to record that value and see the difference. And that is the same difference we would see if we were trying to make a measurement, but it's easier to see it on the gauge than it is on your digital source. So it's kind of a bit of a trick, but it's highly recommended. Let me change my screen here. There we go. Alrighty. Most of the calibration equipment that we have that we've talked about so far is just on the pressure source side. There is a measurement component that we haven't talked a whole bunch about, but if you're doing a transmitter that provides 4 to 20 milliamps out as a measured value of the pressure to the process, sending that 4 to 20 into your process for control, when you go to do a calibration, you need to consider the electrical part of that calibrations device. Ultimately, you'll have a loop accuracy, like what is the overall accuracy of my loop that I'm willing to tolerate. And when you bring your calibrator up, again, we suggest 4 to 10 times being 4 to 10 times more accurate, but consider the electrical portion as a part of that. Okay, many times this is overlooked. We just look at the pressure calibration specifications and we say, yes, I have enough accuracy, and then they just go. Granted, the electrical side is typically more accurate than the pressure will be. It's just a little bit easier to measure and measure consistently, but it's something you should still keep in mind. Finally, one of the other tips we want to bring to your attention before we move off of this section and move to something else is automatic data collection. Calibrating pressure can be complicated. You can have a pressure pump, a pressure measurement device considered our standard. We'll have hoses and fittings, and to make all those connections work, we'll have wrenches. We will have maybe potentially another calibrator or a combined unit that'll measure the 4 to 20 milliamps. Maybe we have a HART communication connected all to that. When we start to have all these different pieces together, we start to run out of hands for the pen and paper that we're going to use to record the actual values. So if you can use a calibrator that has documenting capabilities, that's one less thing to worry about. Also, when we can take that information and lock it into the memory of the device, the transcription errors are gone. You know, writing an 8 in the field and having it come back and look like a 6, those type of errors go away. And ultimately, when we use a documenting calibrator, you'll find that they're typically 2 times faster than using a traditional system. So if I have a lot of pressure calibrations to do and I don't want transcription errors, it makes a lot of sense to move to a device that has the ability to gather and capture that information for us. Another really nice thing about it at the end of the day is it can generate a calibration report with all your as found, as left data. Let's talk about some technological improvements, and we have some other things to get through, so we'll get it going here. Fluke has generated this pressure application note. You can download it from that particular link that you see there. It's not pretty to write down, but if I'm not mistaken, there may be some handouts available on the side where you can see the information. You can download any of those handouts today, it's not a problem. And if you don't get to it, you can always ask ITM for a copy. This is I'm going to say 20-page application note that will run through all of these different types of calibrations for you. It's a nice wide variety, and unfortunately, we don't have the time today to go through them all. So I've selected a few that we're going to have a quick test and quick discussion about. So pressure switch testing, on each one of these, I'm not going to go through the steps on the side. I'll let you read those individually if you want to. But what I'd like to do is just kind of give us an overview and concentrate on the tech tips. So when we do a pressure switch, we'll make our pressure connection and our electrical connection. We have the opportunity to connect to either a wet or a dry switch. A dry switch is a switch that just gives us contacts. A wet switch is tied to the electrical system and provides either a voltage or some other signal back to us that we need to measure with a meter. When we make those connections, the best practice part of this is to pressurize close to your switch point. Make enough room in your pump previous to this to provide a vernier adjustment over that switch point. When you get a switch change in your meter or whatever you have connected to your switch, use your vernier to adjust it back out. You would have recorded what the switch point was. As you record it back out, it'll switch again. And those differences that you have between the switch points is what we call deadband. And I'm sure you've heard the term before, but just as a reminder, deadband is going to be the difference between the set point and the reset point. You're going to want a bit of room there. Every system is different, but knowing that difference will allow us to make sure we operate our systems that are dependent on switches so that the switches don't cycle off and on too quickly, or don't even turn on before it gets too low for the system to run properly. A couple of quick tech tips, excuse me. When you go to do a actual set point and do your calibration, don't just go do it once. We suggest you cycle through that a couple of different times. You may find some differences as to what the set points are, or even what the reset points are, and ultimately the deadband. Obviously, you're going to have to write some value down for what the set point is. And that's something you can talk about how you want to do it. Do you want to take the maximum pressure that it was seen? Do you want to take the minimum? Do you want to take an average of them? I'll leave that up to you on your end, but having that little bit extra data also does lend itself back to that discussion that we had about exercising. And again, it's a mechanical system, so let it exercise a little bit. When you use a multimeter to measure wet contacts, again, wet being a voltage, make sure that your meter can actually handle that voltage capability. Sometimes you'll have a switch that switches 24 volts DC, and then other times you might have a switch that switches 120 volts or 240 volts. And making sure you know that ahead of time, and make sure your meter is set up on that range so it doesn't overrange. Most of our meters are auto ranging, but keep that in mind when you come up with it, and make sure you're doing the safe electrical measurement practices. And use our documenting calibrator to automate switch testing. This tech number 3, I'm going to save to call it an Easter egg at the end. There's a product I want to talk about and how we do it. Pressure transmitter calibrations using HART. So HART stands for Highway Addressable Remote Transducer. It just means a smart transmitter, one that uses a specific protocol to communicate set points to it. Typically, the transmitters will take a pressure in and provide a 4 to 20 out based on a table, and we're going to do a pressure calibration with them. The real trick of all of this, besides making the good connections and getting it to stabilize for you, is make sure that you understand what it is when you're doing a calibration. It doesn't talk about it in here specifically, but if you are doing a sensor trim and the device is not set up to take advantage of that, you can actually be putting the transmitter at a calibration. We have a dedicated app note for this. Unfortunately, I didn't make it available in the sidebar. It does talk about it a bit in the detailed version of the application note that is available today. But if you want more information on how to do smart transmitter calibrations, we have videos online and we have a bunch of other resources. The tech tip I want to focus on today, this is just a good overall tech tip. I know it's kind of hidden in this particular slide, but it really is a tech tip to talk about debugging your pressure connections at the shop before going into the field. Any tools that you are going to need, again, if you're not carrying your spare parts with you or any other wrenches or whatever the case may be, it's going to be good to be able to kind of do a dry run at the shop. And also, if you have any problems that come up out in the field, they're field related, not just generally with the pieces of equipment. Another tech tip to consider, a lot of pressure transmitters, they don't respond instantaneously. They have built-in delay, and you can actually control that delay with your HART programming. So if you know the delay of the transmitter, or you can read it from the transmitter using your communicator built into the 754 on your own as an old handheld device, it allows you to keep that in mind when you make a pressure change, that you should wait for the transmitter to respond. This is a fairly detailed calibration, but I like putting it on the display because it covers many different types of calibrations in one. So custody transfer is a great example of, the types of calibrations that are required. It involves pressure, it involves temperature, there's calculations for flow and volume. They have computers doing all of this information on the fly, and ultimately the goal of these gas custody transfer or liquid custody transfer equipment is to say, I've given you this much volume and you've received this much volume. It's kind of a point of changing ownership of the goods that are in a pipeline. So from a calibration point of view, let's get started and talk about the actual device itself. So we have a 721. It happens to be one of our dual pressure calibrators. It has inputs for 2 pressures. It has 4 to 20 milliamp sourcing capability, and it also has an RTD measurement probe. So it's kind of uniquely designed to handle these types of applications. But what you would do is you would pressurize it on the low pressure side using a hand pump and measure the 4 to 20. Okay. As it says in the tech tip, every manufacturer of flow computers have specific test procedures. So I'm just being very generic, but I just wanted to highlight that you go through the process that they suggest, either closing off valves or whatever the case may be, and you do a low pressure calibration. Okay. Then there's a low pressure differential that gets done. So you vent one of the connections and make another connection and do a low pressure adjustment. Typically, we're talking inches of water, and that is an example of the pressure difference that's happening within the stream of fluid itself. The low pressure calibrations can be easily affected by temperature of the environment. So if you are using dark tubing and you're in a sunny environment, you can get these low pressure changes by the sunlight heating up the tube and creating a volume change. So they suggest maybe potentially using clear tubing, and there's not a lot of volume associated with it. So the larger the tube, the more stable your measurement will be. And if you have the opportunity to use a dedicated low pressure pump for these applications, the pump that is in this picture right here, I couldn't change this picture out, but it's a 600 PSI hand pump, pneumatic hand pump. But if you have something that can do lower pressure and has a longer vernier control, these may look old. They've been around for years and years. We have our own version of it, but they still are very, very good. Some people call these bicycle pumps, and they're very good for low pressure applications, maybe even better than these fancy 600 PSI pneumatic hand pumps. Okay, so you make your pressure connections, then you do a static pressure calibration. Again, getting back to that term that I gave earlier, static is what is the pressure in the system while, even though it's flowing and I'm measuring a differential, what is the overall pressure? And on some pipelines, it might be 1500 PSI or 1800 PSI. It has to do with how much pressure is in the system. In this particular case, we're using a gauge just to show that we can do it with a simple gauge connection. The nice thing about this device, the 721, is it has a high pressure port on it as well. So not only do we do the low pressure side, we can switch it over to this port and do 3000, 5000. There's a bunch of different ranges that you can buy the unit and have it set up to do for you. So again, that kind of, I just highlighted what tech tip number 1 talked about. Tech tip number 2, again, allow the pressure to settle before entering the calibration points into the computer. The computer itself will, these static pressures are pretty important for the overall calculation and getting a good value. It's important to be able to do that correctly. Temperature calibrations. So temperature, again, getting back to how temperature and pressure relate to each other, taking a temperature calibration is critical. The probe, as you notice here, it says RTD probe. This is kind of what I would consider the recommended practice. Depending on your temperatures, Fluke has a whole series of other probes that can give you more accuracies. We have SPRTs. We have PRTs, so that just means precision RTD. There's a bunch of different terms, but we have other probes that are available. This is the probe that works with this unit. So if you've chosen to buy one of these to do gas custody, you got the low pressure, the static pressure on the high port, and then you can also use the 700 RTD probe. If you want to make more accurate temperature measurements for custody transfer, we have a full solution of temperature measurement capabilities. And that was the previous session. And if you sat in on it, you would have seen some of the stuff that we have with regards to dry blocks and automatic calibrations. If you have any questions on that part of it, just forward it off to ITM and we'll help you out. Let's talk about simple, easy ways to get calibrations done. Not every gauge that you have in the field needs to be calibrated in the field. If you have a way to calibrate equipment in a shop, there's some really inexpensive and effective methods for generating pressure that is nice and clean. And this particular technician he's wearing a t-shirt. Life is good. And what this is a simple gauge comparator. So what the gauge comparator does is it pressurizes both sides of the system at the same time. You've got a great vernier control for pressure. And as you roll it up, you'll see both numbers change. You can write the values down. Super easy to use. You can use quick connects on these devices to change out your units under test and get several going at once. If you really wanted to, you could build a manifold and do a whole bunch at once. They're super easy and easy to clean, and I suggest you consider buying one for the shop just to handle some of the workload there. And maybe even on analog gauges, as an example, they still have a great place. They're inexpensive and they do a great job of giving you a pressure value. But if you do want to calibrate them, you can put them on a rotational cycle. Alrighty. I notice we're coming up on some time here. I wanted to, introduce you to a product that we have, and the points that are showing on the display right now are actually some feedback from customers. Pressure calibrations are typically not easy to do. They're typically done in the field. There's leaks involved. You've got a lot of equipment on the go and your hands are full. Generating an accurate, stable pressure across the entire pressure range can be difficult. And then again, testing pressure switches and achieving some kind of repeatability is difficult. I talked earlier about cycling 2 or 3 times. If you start seeing big differences and you got to cycle them 5, 6, 10 times, it becomes very frustrating. So back about 4 years ago, 4 or 5 years ago now, we introduced a 729. It's an automatic pressure calibrator. It has a built-in lithium-ion battery, and it has the ability to receive a set point from you. I mentioned earlier that we have these pressure controllers that are lab grade. We've taken the technology out of that and put it into a handheld device. And we have models that are 330, 300, and also a 100-pound version. And what you do is you simply go up to the device. It's got a HART smart communicator in it, so it can talk to the device, figure out the calibration span and range, set itself up to do a calibration. And as it's shown, this person here is using a phone to read the device. But basically, you can do a fully automated calibration, record the results, and feed it back into a computer. So simple, easy. There's one connection for pressure, one connection for electrical. It's got this very unique 2-magnet Y-shaped hanger that allows it to hold the unit up, so it's out of your hands. And we've put this in the hands of several customers, and they're finding and reporting back to us that they're able to do pressure calibration somewhere in the order of 2.5 to 3 times faster than ever before. So if you have a lot of pressure calibrations, or you're on a turnaround, or you want to be able to do calibrations quickly, this product typically pays for itself within a year. All right. So let's pull it all together and get to questions. We all know that pressure calibrations are valuable to your operations, and selecting the right equipment depends on your pressure workload. And look for opportunities to make improvements in your pneumatic and hydraulic applications. We've shown you a bunch of things today, a bunch of tips, and hopefully we've reached some of the goals of that today to give you some understanding about the potential sources of instability, understanding that resolution itself might not be best. It's a good idea to strike a balance between resolution and accuracy. Avoid contamination, work as clean as possible wherever possible. Exercise your equipment prior to doing calibrations. And finally, the last page, be engaged with the potential for improvements. There's technological improvements all over the place on a regular basis. And I would say that even simple things like pressure calibrations, even though we're using, bicycle pumps today, there's still other sides of the spectrum. There's some significant room for improvements. Coming today to a webinar and spending some time with us, we appreciate it, and hopefully you've got something out of it. And if you have any other questions, feel free to reach out. I'm going to put it on the final screen here, and if there are any other questions, I'll take them now.
Perfect. Well, thank you very much for the presentation, Ken. We'll keep your webinar off for now, so everyone, you'll be staring at my lovely face while Ken answers any and all of your questions. So this is the time to take advantage of having an expert like Ken with us today to answer any and all questions that you may have. So I encourage you to use the chat feature, send in as many questions as you can. We have a little less than 10 minutes to get to anything and everything. If by the end of the Q&A session we were not able to get to your questions, I'm going to invite you to take a look at our website, itm.com. You'll find our complete list of products, all of which Ken touched upon, as well as many others and many other modules and specific instruments for your desired application. So pricing, availability, data sheets, manuals, and most importantly, if we aren't able to get to your questions today, you'll have our Contact Us page where you can find all our coordinates on contacting us via email, phone, or chat as well. So again, please use the chat feature. We did have a few questions that came in during the presentation. So first of which, what would be the recommended calibration interval for specific calibrators?
We get this kind of question fairly regularly. Recalibrations usually means your equipment has to be sent back. It gets recalibrated and sent back to you, so it's out of service for a while. People are, maybe potentially looking to reduce costs by maybe extending calibration cycles. I would say that if you have the ability to extend your calibration cycle, it has to do more with your risk tolerance. The last thing you want to do is send a piece of equipment back for calibration and find that the unit that you've been using as your standard is out. That turns into a pretty, depending on how you're regulated, a pretty extensive set of corrective actions. Usually what you have to do is go through your workload in reverse order. So finding that reverse order might be difficult until you find that your units under test are starting to come back into calibration, and might give you an idea when that happened for you. If you've extended your calibrations beyond a year, year is kind of industry recommended standard. If you've decided to extend it beyond a year into a 2-year time frame, again, that just is extending your risk that you've maybe been using a standard that is not accurate. And that's ultimately what I can say about that, I guess.
Okay, perfect. Something that you did allude to, but is something that I can speak from experience that we do get asked a lot as well, is with these types of calibrations, using these types of calibration tools, can they replace a calibration service like one that we offer at ITM?
I would, and it comes down to accuracy and turns ratio and everything. If you're taking a Fluke 700G pressure gauge and you do the math on it, you typically need, again, 4 to 10 times more accuracy, and you're not going to find, what winds up happening is accuracy becomes more expensive the higher you go up that chain of traceability. If I were to quickly go back to one of the very first screens I had, I'm going to leave it on the display here. Okay, here we go. So the process instruments, that's what you have, that's what you're calibrating. Your working standards are what we consider your standard, that like your 700G. These secondary standards, these are the ones, or maybe even primaries, depending on what ITM's invested in. They are going to be 10 times more accurate. And unfortunately, from a pricing point of view, they're typically 10 times pricier. So you can imagine as you work up this chain of traceability, it becomes pretty expensive. If you had an in-house primary standard, and to be honest with you, some people back in the day used to use a deadweight tester as an in-house primary standard. And by today's technological standards, I would say that some of the digital equipment that gets sold, like a 700G or even your transmitters in the field, have a tendency to encroach on what a deadweight tester can do, unless you've really spent a lot of money and you've got a nice clean room and you've got a really nice piece of equipment. I don't know if that answers the question, Chris, but I would suggest that for the cost, you'd have to have a lot of workload and have to set up a lab and have all those other traceability issues. So
yeah,
it makes more sense just to let you folks do it.
And I mean, just to kind of elaborate a little bit on taking a little bit of my own expertise, would be the type of service and calibration that we offer would kind of go hand in hand with the calibration equipment that you use for the gauges and any type of equipment that you're using these calibration tools to calibrate in the field, as you mentioned. Whereas, I mean, we can offer the calibration services for the gauges and everything themselves, but they're our services can go complementary with the calibration tools as well. Another just quick reminder, we've got a couple minutes left for questions. We do have a couple more. Please use the chat feature. If we don't get a chance to get your question answered today, we will, if it's questions in the queue, we will address it after the webinar, as well as I mentioned, you can visit us at itm.com, as you see on the slide right now, to find all our contact information, products, availability, etc. So another question that came in, can you calibrate a 10 PSI gauge and a 300 PSI gauge with the same calibrator?
That's a good question. The interesting thing about the way products are specified is it comes down to a discussion between if it's been specified to a full scale accuracy or a percentage of reading. You can imagine if you had a 300 PSI gauge and it was specified to, let's just pick a number, 1% of full scale. That means at 300 PSI, it's going to be accurate to 299 or 301 PSI. Unfortunately, because you take that full scale accuracy, it drives it all the way down. If you're trying to calibrate at 10 PSI, it's either 9 or 11. That would be the range of accuracy. If I had that same 1% of reading, you would notice that at 300 PSI, the numbers would be identical, but at 10 PSI, it would drop to 9.9 and 10.1. So can you just ask your question again, Chris? I just want to wrap it up properly.
So just can we use the same type of calibrator to calibrate a 10 PSI gauge and a 300 PSI?
Okay, so just be aware of your calibrator's accuracy and make that decision on paper before you go out. Don't just pay attention to a banner spec. There might actually be temperature coefficients and a bunch of other things. So yeah, just know your equipment. That's probably the easiest way for me to explain it. Some can, some can't.
Absolutely, I think that sums it up pretty well. So we are getting to the top of the hour. To be respectful of all of your time, we'll wrap it up there. We do have a couple questions that were left in the queue, which we will address directly with you after the webinar. So Ken, I want to thank you very much for a very informative and great presentation once again.
Welcome, thank you. And thanks for everybody's attendance time today. I hope it was valuable.
And on behalf of ITM University, we want to thank you for attending today. As just mentioned, we hope that you found it informative and helpful. ITM Instruments is here to help you in any way that you possibly need. Simply visit our website, itm.com, for anything that you need in terms of pricing, availability, some of the products that we talked about today, or any other products that you need for your specific applications as well. You'll find product data sheets, manuals, pricing, availability, and most importantly, our contact information on how you can get connected with one of our sales support staff and our technical support staff to answer any questions that you may have on a technical standpoint. At the end of this webinar, we'll have a very short survey that we'd like you to complete. Your feedback is very important to us and will assist us in improving our webinars and bringing you topics that you are interested in. Also, we have a full list of upcoming webinars on our website as well. If you go to the training section of ITM.com, you can find a full calendar and schedule of the upcoming webinars and all our topics. And don't forget that as a thank you for attending today, your name will be entered into a draw to win $100 on your next online order. The winner will be announced via our social media channel, so please be sure to check us out there. Ken, I want to thank you very much once again, and thank you all for attending today. We wish you a great rest of the day.
Great, thank you very much.